Welcome to the Explainer. Today we are diving deep, and I mean really deep, into the architecture that basically runs the entire AI world right now, the Transformer. It all started with a groundbreaking paper back in 2017 called Attention is All You Need. And let me tell you, that paper completely flipped the script. It threw out the old way of processing language word by word and gave machines a way to understand the whole picture, all at once.
All right, so here's our game plan. We're going to unpack this thing layer by layer. First, we'll talk about why the Transformer was such a revolution. Then, we're going to pop the hood on the architecture itself. And finally, we'll get into the real heart of it all, the technical mechanics of its incredible engine, self-attention. You know, before the Transformer came along, language models had to read text in a straight line, one word after another. Imagine trying to understand a complex story by looking at it through a tiny little pinhole. That was the reality. And it created these massive bottlenecks, not just in speed, but in memory. By the time the model got to the end of a long sentence, it had already forgotten what happened at the beginning.
The absolute game changer here was parallelization. So older models, like recurrent neural networks, had to process sequentially, which is a huge limitation. But transformers, they can look at every single word in the sentence at the exact same time. Now, this isn't just about being faster. It's a totally different way of thinking. It lets the model build this intricate web of connections, understanding how every word relates to every other word simultaneously. That ability is the secret to understanding really deep, nuanced context.
So at its core, the original Transformer was designed for what we call sequence-to-sequence tasks. The classic example is translation. You put in a sentence in one language, and you want to get it out in another.
Right. An input sequence goes in, and output sequence comes out. Looks simple from the outside. But what is actually going on inside that black box? Well, if we pry it open, we find two main parts working together.
And here they are, the encoding component and the decoding component. Think of the encoder's job as being the reader. It meticulously reads the input sentence and distills all of its meaning into a set of highly contextualized numerical vectors. Then, the decoder takes over. Its job is to use that condensed information to generate the new sentence, word by painstaking word.
Now, each of these components isn't just one thing. It's actually a stack of identical layers. The original paper used a stack of 6. So let's zoom in on a single one of these encoder layers. It's got two key parts. First, the star of the show, the self-attention mechanism. And second, a pretty standard feed-forward neural network that takes the output from the attention layer and does some more processing. It's the interplay between these two that really starts to create the magic.
Okay, this is it. The single biggest breakthrough in the whole paper. Self-attention. It's basically a mechanism that lets the model, as it's looking at one word, figure out the importance of all the other words in the sentence. It's like giving every word in the sentence the ability to talk to every other word.
Just look at this sentence. For you and me, it's a no-brainer what the word "it" refers to. But for a machine? This is a huge problem of ambiguity. How on earth does it know that "it" means the animal and not the street?
This is precisely what self-attention solves. As the model processes the word "it," self-attention lets it scan the whole sentence and score the relevance of everything else. It sees that animal and tired are highly relevant clues, so it literally bakes that understanding into its mathematical representation of "it," creating this deeply context-aware vector, a string of numbers that now represents it as, essentially, the tired animal.
So how does this actually work under the hood? How does it do the math? Well, it's all done by generating 3 very specific vectors for every single word in our sentence: a query, a key, and a value.
So where do these vectors come from? Well, we start with a basic numerical representation for each word, called an embedding. Then, and this is the critical part, we multiply that embedding by 3 totally separate weight matrices. We call them WQ, WK, and WV. These matrices are the real secret sauce here. They are just full of numbers that get learned and fine-tuned over millions of examples during training until they become experts at producing the perfect queries, keys, and values.
Okay, so here's the core calculation in 6 steps. First, you take the query vector for the word you're focused on, and you compute its dot product with the key vector of every other word. That gives you a raw similarity score. Step 3 is super important for training. You scale those scores down by dividing by the square root of the dimension of your key vectors. This just keeps the math stable. Then you run those scores through a softmax function, which turns them into nice, clean probabilities that all add up to 1. This is your attention score, literally what percentage of attention to pay to each word. Finally, you take those scores and multiply them against each word's value vector, and then you just sum it all up. What you're left with is a brand new vector for your original word, one that is now packed with contextual meaning from every other word it just paid attention to.
And this is the whole thing, boiled down into one beautiful, famous formula. It might look a little intimidating, but it's just a matrix representation of the 6 steps we just walked through. It's what allows a GPU to perform this entire complex dance in a massively parallel and efficient way.
But of course, they didn't stop there. Instead of just calculating attention once, the authors came up with an even more powerful mechanism called multi-head attention. This gives the model an even richer way to understand relationships.
I want you to think of it like having a panel of, say, 8 different specialists all looking at the same sentence. Each specialist, each head, gets its own unique set of those WQ, WK, and WV weight matrices. This means each head can learn to specialize. One might get really good at tracking subjects and verbs, another might focus on pronoun relationships, a third on causal links. They're each looking at the data from different angles, or what the paper calls different representation subspaces.
So if we go back to our example, when the model is encoding the word it, one of those attention heads might learn to put a really high score on the animal, figuring out who it is. At the exact same time, another head might learn to focus on the word tired, figuring out why the action happened. The model's final understanding of it is then able to blend all of these different learned relationships together at once. So, now that we have this incredibly powerful building block, let's look at how it became the foundation for all the famous AI models we talk about today. Because what's really cool is that not all of them use the full architecture. Different models use different parts to become specialists at different jobs.
The original model from the paper used both the encoder and decoder stacks, which is perfect for translation. But then you get models like BERT. BERT throws away the decoder and only uses the encoder stack. This lets it look at text in both directions, forwards and backwards, to get a super deep, bi-directional understanding. That makes it amazing for analysis tasks like sentiment or search. And then you've got GPT. GPT does the opposite. It uses only the decoder stack. This makes it an expert at one thing, predicting the very next word. It's autoregressive, meaning it takes its own output from the last step and feeds it back in as input for the next step. This makes it a phenomenal text generator.
And here's the biggest takeaway. This incredible mechanism for weighing and calculating contextual relevance, it's not just for words anymore. This fundamental concept is now being used to understand images, to process audio, even to analyze protein structures. It's just this incredibly powerful, elegant idea that is broken out of linguistics and is now transforming all of AI. And it really makes you wonder, what's it going to learn to do next?